Hi, and welcome to ArcGIS API for Python, Mapping, Visualization, and Exploratory Data Analysis. My name is Andrew Chepkowski, and my colleague David will be along shortly, and we'll be talking about the various ways we can do visualization, exploratory analysis, and mapping on both spatial and tabular data. So let's jump right into it. The question arises is, why do we even want to talk about visualization? Aren't exploratory statistics enough to describe my data? Why do I care that I need to graph something? Well, let's give 4 data sets with nearly identifiable descriptive statistics. So we have a mean of 9, a sample variance of 11, mean of x of 9, mean of y of 7.5, sample variance of 4.125, etc. And we have the same linear regression line for all 3 data sets. And r squared is 0.67. And here's the data in the chart. So we're going to go ahead and take this information and put it into NumPy arrays. So when we go ahead and we draw this data that we had before, you notice that the data looks completely different. So we have in the upper left-hand corner, we have this linear model and the data seems to fit. And then, we have these curved lines and one's vertical, and then we have another line in the lower left-hand corner with one outlier. And this is called Anscombe's quartet. And it's basically to demonstrate the importance of graphing data before you analyze it. And then it shows the effects of outliers and other influential observations on statistical properties. He basically wanted to counter the impression among statisticians that numerical calculations are exact, but graphs are rough. And with this, we were able to show and prove that graphs aren't rough. They can actually give you a good insight into your data. So let's go take a look at how we can visualize our data. Data visualization within Pandas, you have a lot of options. And I'm not talking spatial, just spatial. I'm talking graphs, diagrams, charts, pictures. There's a lot of different ways to represent information. And some of the common packages that we use are Matplotlib, the Pandas visualization that's built in, Seaborn, ggplot, Plotly, which allows us to create these interesting interactive plots. With Matplotlib, let's start with Matplotlib. And Matplotlib specifically is a Python 2D plotting library that produces publication quality figures. And it's very low level, so there's a lot of functions, but it's been around for a long time and it's considered a mainstay. You can go to matplot.org to find the documentation, and you can install it either using pip or condas, whatever your flavor is. And let's take a look at how simple it is to create a chart using Matplotlib. So we're going to use NumPy to create our data. Arrays to create our data, and we're going to import NumPy and matplotlib.pyplot as PLT. We do the as PLT because we don't want to write matplotlib.pyplot every time. So we're going to have some data. We have our X locations and then our 3 Y data sets. And we're going to do a VStack and stack all our Y data. And we're going to provide it some labels. And then we're going to create our chart. So we're going to create we're going to do plt.subplot, and this gives our figure an axis. We're then going to add our stack plot to the axis with our data sets and labels, append a legend in the upper left-hand corner, and show our results. So let's go ahead and run that. And here we have our data shown. Upper left-hand corner, we know where the data is called Fibonacci even and odds with the colors associated with it. We can take these same concepts and we can use the Pandas visualizer. And what we're going to do is we're going to leverage information within a series, which is a one-dimensional array within Pandas, or on the data frame as itself, which is a representative collection of named one-dimensional arrays that essentially represents what could be compared to an Excel spreadsheet. So let's do an example from the series object. So we're going to create random data, 1,000 points, and we're going to set the index for a range of values. So we're going to do pd.range starting at January 1st, 2000, and we're going to have 1,000 periods. We're then going to go ahead and plot, call the come sum, and then we're going to plot that data. And let's take a look at what we get. And what we get is a line chart by default by not passing in the any properties. And notice it gives you that time feel of values shifting over time, sort of that you get with stock market prices of a stock, how they jag it up and down over time. Seaborn is another very useful library, and it's one of my favorite to use because it takes a lot of the nastiness of Matplotlib and produces a nice high-level interface using encapsulation, and it draws attractive and informative statistical graphics. And you can find the documentation at seaborn.pydata.org. And it can be installed just like the other packages using pip or condas. So we're going to import Seaborn, so import Seaborn as SNS. And we're also going to import Matplotlib, just like we did before. I'm going to go ahead and set a style that's predefined, and there's a whole collection of them that you can examine. But in this case, I'm going to use the white grid background. I'm going to load, Seaborn comes with some data sets that allows you to work with data. In this case, I'm going to load diamonds. And I'm going to draw a scatter plot and plot the points, the sizes to different variables in the data set. And I can do this really easily using the scatterplot function in Seaborn. So I set my X and Y values, so clarity and price, and then the hue, which is going to be color to clarity, and then the size is going to be the depth of the diamond. We pass in our diamond data set our access, and we're ready to draw. So let's go ahead and run this. You can see as the carets go up and the we can see the effects that the variables have on our point data sets, from the depth to the actual hue of how the information looks. So that means not only are we showing information about not only are we just showing the scatterplot information, so the distribution of everything, we're also showing additional features by affecting the opacity and the color scheme that we have going on these actual points. So we're conveying more than just about clarity, and depth. We're providing more information than you would get from a standard chart. Let's take a look at another pointer scatter chart, and this is going to display XY coordinate systems on a Cartesian plane. We're going to go ahead and do our imports using Matplotlib again. I'm going to generate some random data in X and Y space. And then we're going to generate some random colors of data based off of our N value, random 100 colors. And we're going to go ahead and also specify radii. So this is going to be the width of those points. So kind of what we were doing before in the previous plot, but we're doing it now using Matplotlib. And the result here is our random data, and then we have our areas, how the radius is for each point that we randomly set, along with colors being changed as well. And it's just another way of how you can compare different styles for different packages. Here's another one that I find quite interesting. This is using Seaborn, and what we're going to do is we're going to plot the survival rate between male and female and class. So we have the lines connecting the same classes between first and male and female, and then second male and female, and third male and female, and the survival rates of people on the Titanic. So if you were a female in first class, you had almost 100% chance of survival, whereas if you were male in first class, you had about a little under 40% chance of surviving. Bar charts are terrible. No, I'm sorry, not bar charts. Bar charts show comparison among discrete categories, and it's a common visualization. So let's take a look at how we can make it. So in Matplotlib, we can we just use a plt.bar, pass in our information, and we can stack various bar charts next to each other. So for each additional bar we call, it adds another bar next to the other one. So for example 1, it's in blue, and example 2, it's in green. Then in Seaborn, we can do similar things. So here's another style. So we set our white grid background. We're going to load some data sets in from tip, and we just call bar plot and pass the information in. Histogram plots are another common way of showing frequency of distribution of a numeric array by splitting it into smaller bins or equal size bins. And it's used to estimate distribution of data. So it's a very important part of statistics. And we're going to import Pandas, Matplotlib, and NumPy. And we're going to read some data in. So we have medium house prices, and we're going to build bins. So we're going to use plt.histogram, and this is going to return n, the bins, and our patches, because we set bins to auto. We're going to set our grid, our x and y label axis, and our title. Then we're going to go ahead and plot that out. So we do plt.yLimit, and we set our ceiling value, and this will allow us to show our graph with the frequency distribution on it. But we can do it even easier in Seaborn, so we can just do displot and then pass in that value. And we can see we get pretty much the same exact plot minus the upper limit that we did with the y limit that we set on PLT right here, because we have a little extra white space. But we were able to do what we were able to do in multiple lines of code, plt.hist, we can do it in one line of code with seaborn.displot. This is the chart that's terrible, and this is the pie charts. And pie charts are terrible, but they're a classical way to show composition of groups. It's not recommended. You should never use it if you don't have to, because they're commonly misleading. When using a pie chart, it's highly recommended to explicitly write down the percentage values or whatever it's representing for each slice. So let's go ahead and bring in some data. I'm going to pull some data down from GitHub, and I'm going to group by class size for these types of vehicles. I'm going to pull in the information. I'm going to go df.plot. I'm going to say I want the kind of a pie chart and the figure size. I'm going to do plt.title, pass in the title, pie chart of vehicle class is bad, set my y label to nothing, and then show my graph. And here we have the breakdown. But what you see in this graphic is that it's hard to tell the difference between two-seater and minivan, or subcompact and midsize, and maybe even pickups. Are they all the same size? We don't know. This information wasn't conveyed. So if we have to use pie charts and we want to inform the person of the true values, we should label everything, and the data should be easy to read and understand. So let's go ahead and take that same data and do the same group by. And this time what we're going to do is we're going to add the text to it. So now when we go ahead and look at it, we have a legend that represents to each color, and we can see our pie charts. And here, the point of my pie chart was that I wanted to highlight subcompact cars, so I sort of skewed that off to the right while all the other pie charts were in there. And people can quickly see that, okay, this is 15% of the pie, whereas compacts are 20% and mid-size is 17.5, and the same with pickups. So the three that are very close, we can see they're actually different. Oftentimes we have data that deals with that overlaps each other. And Seaborn has an interesting plot called strip plots, and allows us to jitter the data left and right of the exact location, so the user gets a sense that there's overlapping data on top of it. And we can see the results here. So this is we have city miles per gallon, and then highway on the Y, and we can see how the points sort of line up vertically for these data points. And especially if you look at the X value of 15 or 13, you can see that we have a lot of points that overlap there. So we use the jitter function on these plots to offset the various points. Another way to convey information is heat plots. And they're normally colored by intensity of value. And the common application of this is correlation matrix, or if you need to emphasize some data. Maybe you have a data going from low to high over time and you want to show that. So let's take a look at something and let's look at this data. So what we have here is I created the number of, I used the flights data set that's provided by Seaborn, and I'm going to pivot my data and then plot it as a heat map using SNS, which is Seaborn heat map. I pass in my data and I annotate it so people know what the time is and the year with the counts in the middle. But you'll notice one thing about this chart is that even though it's labeled, a lot of times when you do plots like this, people expect low values to be lighter colors and dark values to be higher values. So what I ended up doing here, and the misleading thing that you see on this graph, is that the high value of 622, which is the highest value, is light, and where the dark values, the low values, are low. Now we can sort of flip that around and adjust the color scheme here, and this time we're going to take the power of pandas, and we're going to use that, and we're just going to set the style for our gradient for our and we get the same look and feel here. And what we have is that we have our low values, which are showing up in white text, and the blue value going to our high values that are shown in red. So it shows that the more intense the value, or the higher the count, darker the value. So just to summarize, what we saw here was that there's multiple ways to visualize data outside of just using maps, and there's many ways to tell the message, but you want to craft your visual message to meet your needs, but you don't ever want to mislead anybody. So with that, we're going to go on and move on to spatial visualization. With spatial visualization in the ArcGIS API for Python, we have a submodule called mapping. And this module is going to allow us to create what's called a map widget in the Jupyter notebook environment. And these are a set of classes and functions that allow us to interact with web maps, web scenes, and certain layer types such as map services, image services, vector tile. And there's a whole host of functionality that we get. We get the ability to set zoom levels, map centers, base maps. We can go from 2D to 3D mode. We can add layers to the map, like I said before, items, and other information. So let's get started and create a map. It all starts by importing and connecting to our GIS. So I'm going to do from arcgis.gis, import GIS. Then I'm going to go ahead and create my GIS object. So GIS equals capital GIS. This gives me an anonymous authenticated user connecting to ArcGIS Online. And then I'm going to go instantiate a variable named m equals gis.map, and I'm going to put a location in because I don't want to see the whole world, and I'm going to display it by just setting the variable to be m in the Jupyter Notebook environment. And what we get back is a map zoomed to Washington, D.C. extent. That's an interactive widget. I can pan, zoom in, zoom out. I can rotate by holding the right mouse wheel and spin the map around. This can all be done programmatically. There's also interactive buttons that zoom in and out on the button, and there's a way to change between 2D and 3D mode. Now, we're going to look at it from a programmatic standpoint, not what you can do by hand, and we're going to look at certain properties of the web map. The first thing we're going to look at is the zoom level, and the zoom level is where we're currently seeing based on the tile maps cache, and we're zoomed to level 8. I could go ahead and set that to 15, and you see our map reacted, and we zoomed into that location. I could also go ahead and rotate the map and allow me to programmatically. So I'm going to go ahead and run this and show the map again. And what we'll see is that the map will rotate around 360 degrees till we get back to the beginning where we originally were. Additionally, we can create maps and change their base map. So default, we're seeing this street map base map, but you might not want that and it might not fit the look of your data. On the map object, you could do .basemaps and it returns back a list of default base maps. And we see there's quite a few. This mimics the same exact base maps that you would be able to access on the fly using the JavaScript API. But let's go ahead and see what some of this looks like. So we're going to loop through all the base maps, getting every other one and printing the name out. So we start with the default dark gray, and it's going to pause and then show the various maps. So here's some imagery, and they're all reacting and updating on the map. Now we're going to go ahead and show just some, after we're done doing this, we're going to go ahead and create a map. And in this case, we're going to create a map and we're going to put in a new variable that we haven't put in before, and that's called mode equals 3D. Just interrupt that. Mode equals 3D. And what you see, we zoomed in we're very close to our data, and it doesn't seem like, it seems very similar to our two-dimensional map that we had before. But as I slowly pan out, you see that we're actually visualizing data that's on the globe and not that 2D map. So we can have data that appears in both 2D and 3D format and allows us to work with our scene layer data as well. Let's go ahead and add some data to the map. Let's recreate our map at that 2D layer. And then let's add this web scene in. What I was able to add to this map was city buildings for New York City. And this is all done within our web app right here. So we can add, we get 3D support within the map widget. So not only can you visualize your 2D data, you have your 3D data as well. We can add items to the map. I'm going to create a new map and zoom in. In this case, we're going to be over Netherlands. And we're going to add data to it. So I'm going to get some item, and this is hillshade data. I'm going to go ahead and add it to the map. Notice by passing an item, I was able to directly add it to this map widget. I can remove any layers by calling remove layers. If I don't pass in anything, it removes all the layers. If I specify the exact layer I want, it will only remove that one. Here we have a map, again, over the Netherlands. And I went ahead and I added this information back. And when we do m4.layers, we see that we get the same look that we had before, and with the layer object. And now, if I wanted to remove, let's say I accidentally add this twice. So now if we go back, we can see that we didn't add an additional layer, which is good. So we kind of prevent you from doing that. Now let's look at a different way that we can look at data. We can add in-memory data to it. In this case, we're going to add in-memory vector data. So we're going to query the item for all the world cities that are points, and we're going to pull down the information as a spatially enabled data frame. And when we look at it, we get this tabular format of data with a shape column that contains our geometries. If I wanted to go ahead and plot that, we can go on and do stf.spatial.plot, hit OK, and run it. And it's going to generate a new map, zoom to the full extent of the data. In this case, it's a world data set. And we get to show everything on the map. This is a fully interactive data set that exists in memory. And when we save our map, it will come along with the map itself. So if we decide to persist it to our enterprise or ArcGIS Online. This leads us to cartography within the ArcGIS API for Python. So let's go ahead and grab some data. In this case, we're going to grab line data, and we're going to zoom to Los Angeles, California. We can take advantage of the smart mapping technology that's built into the JavaScript API and pass in simple dictionaries and say we have class size render and the field. Here are lines. The width is determined by the length of each polyline. We can do the same thing for polygon data. Here's an example of doing rendering for a single state. So I'm going to define the polygons that I want. In this case, state name equal to Washington, class color renderer, and the field name. And then we can display that on a map. And we can see we have our data and the class break renderer as well. We can do advanced symbology. In this case, I'm going to build a renderer myself. So I'm going to say I want to do AutoCast. So I'm going to use the JavaScript syntax. And I want the type to be class break. I'm going to pass in the field, the transparency, and the lowest value. I'm going to do an additional thing. I'm going to pass in a visual variable and pass in the web JSON spec information for my visual variable, and then the class break info as well. Doing all that, I can go and I can visualize this on a map, and we can see we get the following results. Now, visualizing it on its own, it's kind of hard to know what everything means, but if we do map.legend equals true, we get an explanation of how our data has been divided up and how to interpret this map. We can also represent render data on numerical attributes. So we're going to take the US county crops data from 2017, create a map and zoom in, entire United States, use smart mapping, provide the field for the color renderer, and display it on the map. And you notice how fast this reacts. We get the same speed and redrawing rates that we get with the regular JavaScript API, because in truth, that's what's on the back end powering this. We can render also spatially enabled data frames, and we saw an example of that earlier. So this is going to use the Pythonic syntax, and we support 5 renderers out of the box. We have simple, unique with arcade, and class break renderers and heat map. So let's obtain some test data. I'm going to grab some information in from cities and plot it on the map. Here's the default look that we're going to get. So here we have the map of the United States. We're going to look over Reno, Nevada. So let's put our spatially enabled data frame and plot it on our map. We're going to have our unique data frame show, our unique points show up. We said we wanted the renderer type to be unique and the columns to be from state. Now let's do the same thing and look at a simple renderer. So we're going to say we want the symbol type to be simple, and instead of being circles, we want it to be diamonds, and we want the inside to be a form of red and the outline to be blues. And we said we get the points here. We can do just like we did with smart mapping. We can do class break rendering. We can render our data on numerical columns. You saw a lot of color maps being passed in, but how do you know what they look like before you use them? We can do from ArcGIS.mapping, import display color maps, and this gives us a visualization of all the different color maps. If you don't want the individual color maps and you just need to get the name, you can also print them out by doing a little syntactical magic for the various color map names and print it out in a nice column. The next part we're going to do is we're going to go on to analysis. And we have analysis of both feature and vector data. The example that we're going to look at here with feature analysis is examining political donations. We're going to go ahead and instantiate and set up our environment and connect to our GIS. We're then going to go ahead and we're going to pull down some information. In this case, we're going to pull down voter data. And here's an example of some of this information. We're then going to call gis.content.import data, and it's going to give us back a feature collection. And now we're able to put this on a map. So let's go ahead and create that and show it on the map. So we're going to create our map and then add our point data on it. So here's our distribution of our donators. Because we want to generalize where we want to, because we want to centralize where our donations are coming from, we're going to do it. We're going to pull in some census tract information and associate the number of donations for that group. So I'm going to grab this Maryland census boundary and examine it for the county that I'm interested in using a spatially enabled data frame. So I do my item.layer, take the first one, do a query, pass a simple where clause, and asdf equals true, display the first 5 records. We can go ahead and visualize that data to see the area that we're working with. There we go, for each track block. Now let's go ahead and use some summarized locations. We're going to take our spatially enabled data frame from the original one and take our points data and summarize within the polygons. we're going to summarize on the field, donate sum. This will give us back a feature collection, and we can visualize this on the map. Where the total number of point counts is more donors within that actual area. To get the age statistics that we need, we're going to take advantage of the Geo Enrichment API, pass our data set in, add these analysis variables, and call enrich and provide the age information that we need. This will allow us to get the total population for the area for both men and women added together, and then we can figure out we're going to clean up the data and get the sum donated by replacing some not a number values with 0. Next, now we're ready to calculate donations dollars per person. We can do some simple algebra on our data frame and visualize it on the map. So we're going to go ahead, create our area, and perform a natural breaks. And we can find the areas where we have that we should concentrate on when trying to get more donations out of them. We can even target the information and make informational plots. For this person that is running for office, we can see that a strong portion of their donation, well, a number of people that they should target based on population is age 55 to 59, because that's for men, and for women 50 to 54 for the people to target for donations. And then, but if we look at donations as a whole, but if we look at the areas for the top grossing areas, we can see that our donations actually skew from the younger generation to 25 to 29. All right, so that's a little bit of feature analysis and how we can couple feature analysis with graphing. So now we're going to shift over to raster analysis. And the first thing we're going to talk about we're just going to talk about generic raster analysis. And it starts by we're going to import ArcGIS and from ArcGIS.gis. And we're going to connect to our online organization. And we're going to pull down some data. In this case, we're going to pull down Landsat data. And this is going to give us a map service with the various layers. So here we have that there. From the item, we can get a detailed description of all the information and display that rich HTML format in there so we can understand what we're looking at. See, we have the types of bands and description about each of those bands as well. One of the most interesting things we can do with the data is that we can visualize it really quick just by displaying it in a cell. So I'm taking the image layer and I'm displaying it, and we get the world imagery shown as a whole. And we can also pull in that table that we had before that we saw from the description test, and we can pull that out of the properties on the Landsat data. And this gives us the various wavelengths, the min and max ranges. We can also display it on a map, the default imagery. Okay, so here's our default display for the Landsat imagery. We can go ahead and take this information and we can apply functions to it. And each of these functions are going to change the way the information is viewed on the screen based on what each function does. Not all image layers have built-in functions, but this one happens to have it. So we can take advantage of those raster functions and adjust our display accordingly. When we apply these raster functions, we get back that different appearance, and we saw it on the map. And it persists all the way through. So once we apply it, the image layer is smart enough to know that I have this function applied and I should always visualize this information this way. In this case, our Landsat data is now visualized in color infrared. We could set an area of interest and restrict by extent of what the information is. So I'm going to geocode an address just to the bounding box of Washington, D.C., grab the extent, and then here's our color infrared imagery. I can set the extent on that Landsat data and clip it to the area that we had before, and we see that we get that. We're going to go ahead and we're going to run this display, and we can also, now that we've set our area and we like the way it looks, we can save it locally. So I'm going to do landsat.export data, pass in that extent, and I'm going to download the image. I could turn around and redisplay it or use it for something else that I need for analysis. We could also specify a larger size and save our image to disk to meet our needs. So here's another way we can display our data. We can export images with those functions applied. So let's apply the NDVI colorized, set the extent, and now we have colorized. I can then turn around and push that out. Or we can, if we don't want to use one of the built-in functions, we could extract our own custom bands. So let's say I want the combination of 3, 2, 1, where 3 is going to be the red, 2, blue, green, 1. So basically flip the colors scheme around. And we can go through and call the extract bands, and then stretch the data out, and we can see how that combination is going to affect the way our raster looks. And this is interesting because all this information is occurring in memory, so nothing is persisting out, and it's happening on the fly. We can clip rasters by geometries. So I'm going to create a simple buffer, polygon, for a location that I set forward. And I'm going to get the subgeography for redlands. I can turn around and I can clip the NDVI by that redlands geometry, create my map, display it on the map, and we'll see that we're going to get a subset of our data information right here. So now besides just clipping it to extent, we can clip it by geometry. Let's pull some Sentinel-2 views in from ArcGIS Online, which is hosted online. There's a wealth of information on there. And we can go ahead and we can filter. In this case, I want to filter where cloud cover is less than 0.01% in the image, and it's category 1. I can then, from that, I can select the images that I want to show, and it gives us the extent. And the nice thing about this is that we could interrogate each one of these geometries and polygons and put them on a map and see the actual coverage to see which is the best one that meets our criteria. We can see that we have 50 that also meet our criteria. And we can also see that this data is fairly recent, as far as January 1st of 2020, all the way up to March 9th. And so let's select the last one, or the newest one, and the oldest one. And this is some things that we can do. We could go ahead and we could take the difference between these two functions and display the results on using NDVI, and then we can stretch it out and display it. So using the new and the last, I'm going to take this data, it's going to do the calculation internally, and it's going to display that map. If I'm happy with the results, I can then take this information and persist it out to my organization. All right, so we're going to quickly flip over and talk about an actual application of raster analytics, and this is dealing with Missouri floods. And what we have here is we have an area in Eureka, Missouri, pre and post flood. On the left, you have an area before the flood, and after, it's currently during the flood. So I'm going to go ahead and I'm going to pull these layers in for the imagery that I have for the pre and post flood. Once I have that, I'm going to create what's called a classifier. And my goal here is to find areas that are flooded by only taking a few samples of my data. In this case, I created 110 little triangles that are going to be my samplers, and I load them in using a feature set. And here they are displayed on the map. I'm then going to use the training classifier, pass in my post-flood imagery and those training samples, use the SVM method, support vector machines, and calculate and create my classifier definition. Once I have that, I can pass my classifier definition into the classify function and get the results. That'll show us the areas that are flooded that happened during this post-flood event. And this information can then be taken out and shared with emergency management so they know where they have to concentrate their areas. All right, I'm going to hand it over to Dave, and he'll take it from there. Thank you.
Thank you very much, Andrew. I'm going to switch gears a little bit and talk through different types of interactive development environments that you can use to develop your Python code. So what Andrew showed you was the traditional Jupyter Notebook format, as well as the Jupyter Notebook server that serves you the notebooks. But new, very recently in the Jupyter project, is Jupyter Lab. Jupyter Lab lets you interact with the same Jupyter Notebook format, but it allows you to do it in a bit more of a full-fledged IDE. IDE stands for Interactive Development Environment. And the Python API supports this Jupyter Lab environment. And I'm going to show it to you because as data scientists and as GIS analysts who are big into visualization, Jupyter Lab really allows you to hone in your workflows and work with visually interesting spatial data in a format that allows for creativity as well as analysis. So it really allows your workflows to be a lot more robust. So if you go to the Python API landing page, let me scroll up to the top of this page. We have our guides and our samples, and one of them walks through using the Jupyter Lab environment. So this is what a workflow might look like in Jupyter Lab environment. You have your notebook tab here, a map over in a separate window, notice different than the notebook, and a CSV. You can still call and add layers to that map. You can visually explore all that, but that is separate from the actual notebook. So there's no more scrolling up and down, and you can do all the same workflows as before. It also has support for the CSV files, as you see here. So again, the same Jupyter Notebook format. If you've authored a Jupyter Notebook using the old Jupyter Notebook server, you can visually interact with it and use it inside of Jupyter Lab. So it's the same format, just a bit more of a full-fledged IDE. So what are some of the other advantages that Jupyter Lab has? Jupyter Lab has a file explorer in this left pane. So you can open up different files inside of this pane. You can open up multiple notebooks all in one window through these tabs that you sort of see here. We'll get more into that later. These tabs, although you can open up multiple of them, are also stackable. So as you see here, you can split these tabs many different ways. I have a CSV tab here that I can move into tabs up there or split it off to the side. And I have different notebooks that I can go through. So tabs can have notebooks, can have CSVs, can even have maps, as we'll see later. Similarly, with the dragging and dropping of windows and tabs, you also can drag and drop different cells. So here, let's say I have a cell from one notebook and I want to move it to the other notebook. It's as simple as dragging and dropping, just like on a traditional desktop, and you can move those cells from one notebook to another. So this is a workflow I actually use a lot, is when I have more of a messy exploratory notebook, and then I have the final one that I want to send to people and have be the final polished version. I sort of copy and paste and just drag these cells over to get the clean notebook that I'm looking for in the end. You also can take the outputs of arbitrary cells. In this case, there is an arbitrary chart here, and you can split those outputs onto a new view, which is very useful. And most importantly is you can, with the GIS map widget that Andrew had showed you earlier, you can actually separate out that map onto a separate issue. So this is a big pain point that a lot of customers ask us about, is when you have that map inside of a notebook, you're making calls to the add layers, and you're scrolling down, making the call, scrolling up, seeing the layer. Oh, look. Oh, it's not there. Okay, you scroll down again, you add another layer. You're keeping it scrolling up back and forth, back and forth. Easy to get some head spin by scrolling all that. So using Jupyter Lab, you can take that map widget and pressing that button in the upper right corner, you actually can move it onto a new view. But instead of showing you just in this web page, so again, this web page here has all the information you need, let's actually run it live. So here I am in the launch screen of my Jupyter Lab environment. I can create a new notebook here. I can open up different things, like make a new text file or a markdown file, and I can go look at all of the different notebooks that I have in my folder. So in this case, I have a few notebooks that I want to show you, and I have a notebook that walks through the Jupyter Lab environment. So just like Andrew showed you before, you input your GIS class. In this case, I'm going to take a web map from ArcGIS Online. And by running this cell, when you give it a second to load, you will see a new web map has been added to the page. And this new web map has the button that you saw before. So this button is not available in a Jupyter Notebook environment, Then in Jupyter Lab environment, by pressing this button, you can now move this map off into its own view. So you can do the same type of panning and zooming inside of this new window, and you also can move up and down in the notebook while having the map off to the side. So again, a very useful way to have you avoid all the unnecessary scrolling. So this button toggles the view in which it's in. There also is, as Andrew showed you earlier, support for web scenes using 3D, the 3D mode of the map widget, and also just viewing web scenes from your ArcGIS Online organization. So as you can see here, you can do the same type of thing, but this is a web scene that you can pan and zoom and the tilt and all of the dimensions in 3D space. And you also can control some of these, some of this functionality instead of with clicking through code. So here I'm going to call map2.toggle window view with the mode of split bottom. And when I run that, I'm able to actually control, oh, I want the window to go to the bottom. Running this again puts the map back up in its original spot. And you can specify all the different types of options that are available. So in this case, I'm going to specify, let me add this to a new cell actually. I'm going to specify mode split right. And now by running this, it actually splits to the right, as you can see. And then finally, we'll do one more. Let's do tab after. So this is a really useful one if you want to sort of open up a map or have a map in a separate view where you don't want it visible all the time, but you want it still there. So by calling tab mode as tab after and toggle widget view, this is now in a separate tab. So this notebook is still taking up the full screen, and you can just switch over to this map whenever you need it. Yeah, so that is the Jupyter Lab environment. You can do all the same Python workflows in Jupyter Notebooks as you can in Jupyter Lab, but it allows you a bit more of dynamic visualization and more sort of data science focused workflows. Great, so that is Jupyter Lab, and I'm going to talk through one more new functionality. This is separate from Jupyter Lab. This is just in the Python API itself, and that is new at version 1.8.0, which is our most recent release, and that is the ability to display local rasters on the GIS map object, the map view object. So Andrew showed you before different raster analysis using hosted feature layers, which is a great workflow. But what if you have some local data? Let's say, what if you have a simple JPEG of Newark, New Jersey? Now, in a traditional GIS workflow using Esri software, you would publish this as a raster. You would have to configure it, and then you would, inside of the Python API, display that raster as a hosted raster. But new at the Python API 1.8 is the ability to create a new raster object. So from ArcGIS.raster, import raster, the path to the JPEG. And since JPEGs don't have spatial information inside of the file, you manually specify the extent. So in this case, just the bounding box of the xmin to the ymin, xmax, ymax, and what spatial reference we're using. I'm also going to specify an opacity of 0.5. But by calling that, as you can see, without ever connecting to ArcGIS Online, I am able to overlay this image file on side of the map. I can pan and zoom in, all the different types of things that you're used to with the map widget. And that's all local without having to publish. So this is really good if you're in a bit more of an exploratory data science phase where you're not sure if you want this to be published yet. You're, have a local image and maybe this is good, maybe it isn't. You can display it locally on the map, do some different visualizations, analyses, and different visualizations with it, see if it's good, and then when you're done, publish up. So a great workflow there. By calling map.remove layers with that raster, you can remove the raster. So just like adding and removing layers with the traditional, much more traditional data. So next, I am going to show you overlaying a TIFF image on the map view. So in this case, I have a TIFF file here, which is of Amberg, Germany, so 09162.tiff. So by calling map.addLayer with this raster, I'm going to call that, and it takes a few seconds to load because this is a very large raster. If you notice, I haven't specified an extent here, and that's because TIFFs have geography information inside of the file itself. And in this case, I'm actually inside of a pro environment, and ArcPy is being used behind the scenes to get that TIFF information, to get that spatial extent information. But as you can see, this local TIFF file was overlaid onto the map. You can zoom in and gain a lot of insight into things, panning and zooming, etc. And this all happens without any, again, connection to your portal or ArcGIS Online. So a great way to just, if you have a TIFF file, as long as it's not too large, throw it on a map. At this time, there is no dynamic downscaling of TIFFs, so you need to be mindful of the size of the TIFF since it loads it all into memory, but you can still overlay them. And finally, this one is my favorite use case for local rasters is, let's say you have a geodatabase, okay? And let's say you have some feature collection inside of that geodatabase, a raster image inside of that, and it's a mono channel raster image. Well, normally, if you were to display that, you would specify it would basically be a white to black or black to white color ramp that would show it. So with black being lower numbers, white being higher numbers, or however it's configured. And that's how you traditionally display a one color map raster. But the Python API and this local raster functionality actually allows you to specify a CMap argument. Now, what is CMap? Let me, instead of talking about it, just show you. So from ArcGIS.mapping import show color maps, I believe it is. So CMaps are Matplotlib color maps that the Python API integrates very well with. Hang on, maybe it's color ramps. I always forget the call of it. Let me just look this up really quick. Here we go. We'll just show you this. So different color maps in Matplotlib, like grays, purples, green or blue, allow for different ways to display color maps. Sorry about that, folks. So there are basically different ways for you to specify different colors depending on the low and the high values. So if you, earlier when Andrew was going through the spatially enabled data frame, he showed you how to use different color maps for the spatially enabled data frame, but this local raster overlay allows for that same functionality. So by running ArcGIS.mapping import display color maps, you can display all the different color maps that you want to use. And so this means that let's say you were to pick this one, PUBUGN_R. At a lower value, it looks like it would be kind of a green, and then it switches to a blue, but then eventually levels out to a white as you get to higher values. So very useful in the spatial enabled data frame, and also very useful inside of the local raster overlay functionality. So what did I just do? I took that local geodatabase mono channel raster. I specified a color map of orange, red, and a light opacity so I could actually see through the raster a little bit at the underlying base map in this case. So by doing that, you can see a very beautiful map of Madison, Wisconsin. This data is about urban heat maps, the phenomenon where urban areas tend to be a little bit hotter. But you can see this is the downtown area of Madison, and it is a darker red. The university campus must not have much data, and as you move outside of the city, you get lower colors. But then there's also Middleton over here, which looks like it has some higher areas or other places up north that have higher levels of heat because of different urban infrastructure. But again, this is not connected to an ArcGIS Online organization, hasn't connected online at all. It's just taken this local geodatabase, and ArcPy is being used behind the scenes, but it reads that raster. It allows you to specify a Matplotlib color map and different opacities, and allows you to display that locally, pan and zoom, and do some more exploratory analysis. So using local rasters inside the Python API is another great way for you to help visualize your data and do different analysis to make better maps and make better decisions. So that's all I was going to cover. Andrew covered the majority of this topic. But for more information about the Python API, you can go to our landing page, which is developers.arcgis.com/Python. That shows you how to install, how to get things set up, different guides and samples that show some good workflows. So a great place for getting started. And also, if you've used the Python API before, a great way to brush up on your skills and learn more and learn some new information and see some different tips and tricks. And then for this virtual conference, as with all of our other more traditional conferences, we have a public Python API repository on GitHub, which contains all of the samples that we normally just post on our developers website. But it also contains all of the notebooks and slides from different conferences in the conferences resources branch. So if you want to view some of the notebooks that I showed you today, or as well as some of the slides from other presentations or notebooks from other presentations, you can go to that conferences resources branch and view the information there. So Andrew and I would both like to thank you for attending our virtual session. And yep, have a great day. Thanks, everyone.